I, Salim, Assistant Professor in Kite Group of Institutions, presenting input-output configuration of a measuring instrument. So first, introduction. An instrument performs an operation on an input quantity. Input quantity may be flow, temperature, pressure, any measurement or designed variable to provide an output called the measurements. The input is generally denoted by small I or capital I, and the output is denoted by small o or capital O. According to the performance of the instrument, it can be stated in terms of an operational transfer function. Here it is denoted by capital G. The input and output relationship is characterized by operation G such that O is equal to Gi as shown in diagram. O is equal to Gi. Our output is equal to G into I. So the various inputs to a measurement system can be classified into three categories. First, the desired input. Second, interfering input. And third, modifying input. So first, desired input. A quantity as shown in diagram. A quantity that the instrument is specially intended to measure. The desired input I produces an output component according to an input-output relationship symbolized by GD. Here is GD. This is my desired input. Here is my GD. Here GD represents the mathematical operation necessary to obtain the output from the input signal. Interfering input, a quantity to which the instrument is unintentionally sensitive. It may be a noise. The interfering input is denoted by IL, would produce an output component according to input-output relationship symbolized by GL. Here is my GL. Then we have modifying input, a quantity that modifies the input-output relationship for both the desired and interfering input. The modifying input is denoted by IM, would cause a change in GD as well as GL. The specific manner in which IM affects GD and GL is represented by symbols GMD and GML respectively. GMD and GML means my modifying input also affect the function GD and also affect the function GL by GML and GMD. A block diagram of these various aspects has been illustrated in this figure. For example, consider a differential manometer which consists of a U-tube filled with mercury and with its end connected to the points between which the pressure differential is to be measured. The pressure difference P1 minus P2 is worked out from the hydrostatic equation, which is denoted by P1 minus P2 is equal to GH. G is the gravity, H is the height, rho m is the specific gravity, rho is the density of mercury, and the pressure differential P1 minus P2 is worked out from the hydrostatic differential equation. Here P1 minus P2, which is the difference of pressure, is equal to rho GH. Here rho m is the density of mercury and rho f is the density of fluid, mass density. Okay. Then h is the height in scale reading. If fluid flowing in the pipe is a gas, in that case rho F is very small than mercury according to the above identity, then we can rewrite this equation P1 minus P2 is equal to rho m GH. Here differential pressure is the desired input, scale reading is the output which is H, and rho m is the parameter which relates the output and the input. So the manometer is placed on a wheel which is subjected to acceleration and scale indication a reading even though the pressure P1 and P2 at the two ends are equal. The acceleration thus continuous to the interference. Here is the example of manometer when we placed stationary and when we place on a wheel and produce some acceleration, and when we tilt this measurement system, in that case our desired input is pressure difference which is P1 minus P2, but when we put this system on a wheeling system and we produce some acceleration to this diagonal type portion is there, and this is produced by the acceleration, and this is the noise in our case. So we have to modify this input according to our system for perfect measurement. So in this case we have P1 minus P2 is our desired input, H is our output, and the density which is density of mercury is our G, based on which we get the output. So in these cases acceleration and tilting produce some interfering input or some noise to our system. So for that purpose we use signal filtering and output correction methods. Here is the another example. In this case we have to measure strain. Here is the strain gauge, and this strain gauge is placed on the one arm of a V-stone bridge. Then here is the 50 Hz AC field also applied to that system. In that case desired input is our strain, interfering input is 50 Hz magnetic field caused by nearby power lines, fields induced voltage in the strain gauge circuit, and modifying input EB. EB is our modifying input. So as we increase the battery level, so the effect of this 50 Hz AC field reduces, as also shown by the figure, because EB is directly proportional to E0. EB because it can change proportionally with the our strain. Okay, so here is the another example of desired input, interfering input and modifying input. This is all about input output configuration of a measurement system. Thank you.